Okay, so today we are going to be doing our final session of new material on simple population models in continuous time. So this is the last of the one-dimensional stuff. We will have the first quiz on Wednesday, and then on Friday we'll just do a review of everything that we've covered so far from the first half or first part of the course. And then next week we will be, next Monday is actually a day in lieu, so there's no classes. And then after that, we'll be moving on to species interactions models. So thinking about where we have more than one population, okay? So today we're going to be thinking about some of the ideas we talked about recently in terms of, say, harvesting and types of bifurcations that can cause these sudden shifts in our populations. And we're going to be focusing on a particular model of pest to do so. So by the end of today, you should understand something called a functional response, what that means, the ideas of attack rates and handling times when it comes to predators, a concept known as hysteresis and bistability as well, and how this relates to these switches in population dynamics. Okay, so in the last lecture, we saw that when we had harvesting of a population, this can lead to a sudden catastrophic collapse in the population, right? So everything's fine, and then the population doesn't just slowly go down to zero, it can suddenly collapse. So this idea of a sudden switch between steady states or equilibria is a common thing in biology. And we're going to expand this to not just think about harvesting, but to think about a particular pest system called the Spruce Budworm, and thinking about what predation by birds might do to these pests. So this insect pest, the Spruce Budworm, it lives in spruce and fir forests in Canada and northeastern USA. And every few decades, usually between 30 and 70 years, there's a sudden outbreak. So there's a sudden massive increase in the population size of Spruce Budworms, and their numbers can devastate lots of mature trees. So the kind of thing we want to know with modeling is like, why do we suddenly get this huge shift? You know, everything's fine for ages, and then you get a massive change in the population size. So let's think about setting up a model that could represent this system. So suppose that we've got a budworm population and it's going to grow logistically. So our usual logistic growth is dNdt is equal to Rn by 1 minus n over k. That's our normal logistic growth. And we're going to have predation by birds at rate p of n. So minus p of n here. And we can write this as, like we did the other day, a growth function, g of n, that's just my logistic growth, minus my predation term, p of n, and that just collapses down into our net growth rate, f of n. So this is just like the setup that we had the other day, right? Rather when we had harvesting, you can think of us as predators in some ways, harvesting fish, say. But we also treated this p of n, when we did it as a harvesting term, we had something of the form qen. So this was just linear in n, right? We're now going to think about what happens if this is nonlinear. So our predation term is nonlinear itself. So the reason for that is because usually if we're thinking about, say, birds predating on this Spruce Budworm, there's going to be a limit to how much the birds can eat. You know, if the population size of Spruce Budworms explodes, the birds need to catch up. They can't eat, more than they can actually consume. There's going to be a limit to this. There also might be limits at the other end. When Spruce Budworms are rare, birds can eat lots of different things. They can eat worms and seeds and things like that. So they might switch to other food sources. So we want to try and capture some of that behavior. So the main thing we want to think about, first of all, is this idea of saturation. So when there's lots and lots of budworms about, the birds can't keep up with them, and they only, they get satiated, they can't eat that much. And so this predation term should saturate rather than increasing linearly. Okay. So the way that we do this in models is to use something called a functional response. And that functional response is basically just telling us the intake rate of the consumer as a function of its food density. So before we had this as being something that's linear, our functional response is going to be telling us how the predation term varies as the population size of the prey varies, okay? So one of the ways in which we can do this is with a function of this form here. So an squared over 1 plus n squared. This is actually something known as a Holling type 3 functional response. There's a type 1, which is just linear, a type 2, and then a type 3. And they'll have slightly different properties. There's a good Wikipedia page on this, actually. So here, what are these different terms? This A is going to be my attack rate. So that's telling me something about the rate at which birds encounter the budworms. So how often they're trying to forage for them. This H is known as my handling time. And this is capturing this idea that birds need to actually catch the budworms, and you need to eat them and digest them, and they're not just constantly consuming them. Okay, so this handling time refers to that idea. There's a delay essentially built in. Okay, so what does this look like? Why don't you guys have a go at trying to sketch what this curve looks like? So think of this as we want to sketch our predation rate as a function of n. So what does this look like? Have a go at that for a few minutes. If you're not sure how to do this, think about what happens when n is very small, say when n is 0, and when n is a little bit above 0. Think about what happens as n tends towards infinity, and that should help you to fill in the bits in the middle, okay? Okay, let's see how you guys got on. Okay, sketch of Pn. Before I sketch this, let's do a little bit of manipulation of that function, see what it looks like. So remember, we're doing n versus p of n. And our p of n is an squared over 1 plus n squared. Okay, so first thing is like, what happens when n is 0? So p of 0 is just going to be what? We're going to have 0 on the top and 1 plus 0 on the bottom. So this is just going to be 0. So I know that I have to go through 0, 0, 0, okay? Next thing is thinking about what happens when n gets very, very large. So as n gets very, very large, I can rewrite this as a over 1 plus n squared plus Okay, so all I've done is I've divided each of the terms within this by n squared. If I do that, then it all stays the same. I have to do the same to everything though. Okay, so what's this going to happen? So this is going to tend to a over as n tends towards infinity. So this 1 over n squared is just going to tend towards 0. So we'll have a over 0 plus So we could just write that as 1 over h. So as n gets really, really large, this is just going to tend to 1 over h, where h is just a parameter, a constant. Okay. Does anyone have any questions about how I did that? Does that make sense? I'll take your silence as that makes sense. Okay. Okay, so what do we know? We know there's a value 1 over h where n gets really, really big. Let's draw on a dashed line. So we know that when n gets really, really big, we're going to tend towards it. We're never actually going to touch it. We're just going to tend towards it. So we know that we're going to be asymptoting something like this. What else can we tell? Well, suppose we've got a value of n that's just a little bit above 0, really, really small amount above 0. We're going to have a times by something very, very small squared. So that's going to be even closer to 0, divided by 1 plus, again, something that's squared that's close to 0. So that's going to be very close to 0/1. So that means that we're going to be increasing very close to this horizontal axis to start with, okay? So it initially starts something like this. So in the end, we now need to fill these gaps in. So we end up with something looks a bit like our logistic curve that we had before. It's not the greatest example of this. I might sketch that again. Let's do this again. It's basically an S-shaped curve. Turns out it's really hard to sketch these things on an iPad Live. Okay. So the question then is, what does this tell us, or how do we interpret the bird's predation behavior as the budworm population size increases? Okay. So if you had this kind of interpretation question, I'd be expecting you to say, okay, what happens when budworms are rare? What happens when budworms are common? And why might that be the case? So let's do this together. Why do you think, let's start with what happens when budworms are rare? Excuse me. Almost no predation. Okay, great. So when budworms are rare, in other words, when n is low, we have almost no predation. The biological reason for this is that birds are likely to switch to another food source. If they can't find budworms, they're not going to be, trying to look for where budworms usually are. They'll maybe go and forage and find seeds or worms, another type of food source. So this is known as prey switching. So switching food source. Okay. What about when budworms are common? So when I say common, let's say very common. So when budworms are very common, what happens? Yeah, so there's a saturation point, okay? So when budworms are very common, the predation rate saturates, and it saturates due to that handling time. It's handling time. And in between that, as the budworms become more common, there's this switching over, so the birds start predating on them more until eventually it saturates. These are the two key points. So what happens when they're very rare and when they're very common? Okay, let's do a little bit of analysis on this model then. So remember we had our DNDT. I'm actually going to write this in a slightly different format now. So if I just go all the way back up to here, where I originally defined it, we have an n on the outside here. And then in my predation term, I have an n squared on the top here. So I can take out a factor of n from both of these. If I take out a factor of n, I'm going to define new functions g of n, capital G, and capital P. Just so I can write these as per capita growth and predation rates. It makes the analysis a little bit simpler because it's slightly easier to draw these curves. It makes that logistic growth rate, and logistic per capita growth rate is going to be linear. And it makes the other one a little bit easier as well. Okay, so we're going to do a little bit like we did the other day with the harvesting. We're going to be sketching our growth and predation curves. And these ones are pretty hard to sketch, actually. So what happens? What we're going to be thinking about is what happens as the carrying capacity of our budworm population increases. Okay, so that means that our predation curve is going to stay the same. Let's draw this on first of all. The predation curve, it turns out, looks something like this. when it's the per capita predation curve, that is. And so this is my capital capital P. And then it's my per capita predation curve. And then I want to think about what happens as the carrying capacity increases. So let's just sketch what this G of n here is just going to equal R times by 1 minus N over K, right? That's my per capita logistic growth term. So this is linear in N. And when N is equal to 0, we have R. This intercept on the vertical axis is R. And then can anyone tell me what value of N this intercepts the horizontal axis, this capital G of N? When is capital G of N equal to 0?
K.
Exactly, yeah. When N is equal to K. So we know, suppose, for example, our K is here. And we're just going to have a straight line that looks like this. And this is my capital G of N. Okay, so can anyone tell me what the significance of this pink dot is? Purple.
P of n minus P of n equals 0.
Exactly. So, and if you're explaining that to someone who's not a mathematician, how would you describe that?
This one equal with that's when the population is stable.
Yeah. So the growth is equal to the predation, right? So that's going to be an equilibrium. Just make sure that's clear. On this side, on the left-hand side, the growth curve, the black one, is above the red one, which is the predation one. So that means on this side, this dashed line, you'll move to the right. And on this side, this red curve is above the black curve. So that means you're taking more out of the population than is growing. So you're going to be moving to the left. And then there's some value, let's call it N1 star, where the growth is balanced by the predation. Note here, this is not the only equilibrium of the system. If there was no individuals, then there would also be an equilibrium as a trivial equilibrium as well. The reason it's not showing up here as an equilibrium is because we are plotting the per capita growth and predation rates. Okay, so this N could be 0, and that's factored out already. That's another equilibrium. But because it's trivial, we don't have to worry about it. Okay. Okay, so that's for K small. So relatively small carrying capacity for my spruce budworms. Okay, let's do the same again, but think about what happens when K gets a little bit bigger. I'll try and cheat if I can here. Okay, so what's this going to look like now? So that red curve stays the same. Remember, our predation has not changed at all. Now we're going to increase this K, and I'm going to pop it over here. Hopefully that's enough. So I've increased this K enough now that there are 3 intersections. call this moderate carrying capacity. So there's an intersection over here, over here, and over here. So just as before, we can think about when are we moving to the left or right. In these yellow regions, the black curve is above the red curve. This black curve is my growth rate. So I'll be moving to the right. And this green shaded region here, the red curve is above the black curve. So I'll be moving to the left. In fact, that's true over here as well. I now have 3 non-trivial equilibria. And I call these N1 star, N2 star, and N3 star. As you can see here, as we've increased the carrying capacity, all this, the difference between this curve on the left-hand side or this graph on the left and the right is that this black line here, I'm increasing this value of K, so that R stays where it is, the value of K increases. We reach a point where we now intersect this curve 3 times. This K increases over to the right, we now intersect that curve 3 times. Because of that, we now have this equilibrium here, this N1 star is still stable, just as it was before. We've got an equilibrium in the middle, N2 star, but that's unstable. And then we have another equilibrium over here, N3 star, which is stable. Stable, unstable, stable. Remember, you can't have 2 stable equilibria next to each other or 2 unstable equilibria next to each other. That'd be like having 2 hills next to each other without a valley between them. 2 hills next to each other without a valley between them, or 2 valleys next to each other without a hill between them. You have to go up before you can come down again. Okay. So what does this mean then? Well, it means that if your population size is less than N2 star, you're going to tend towards N1 star. And if your population size is greater than N2 star, you're going to tend to N3 star. So depending on where you start, depending on what the initial value is of your population, you're going to go to one of these 2 different but stable steady states. And one of these is relatively low and one of these is relatively high. Okay, let's think about one more sketch. Yeah. Yes. Good question. A trivial equilibrium is essentially when there is no one in the population, so when n is equal to 0. These are all non-trivial equilibria because they're all positive. A good question. Okay, let's do one more sketch. I'm kind of running out of room here, so I will try and sketch up here as best I can. Okay, we want to think now what happens when K is even bigger. I always find this one the hardest to sketch correctly. So we're still sketching the same predation curve that we had before. I'm going to sketch it a little bit lower this time. So it goes up and then it comes down and looks something like this. Not the best sketch, but it will do. What else do we have? We have our R. That's where we're intercepting for our growth function. This is my predation term in red, P of n. Okay, we've increased K. So before we had 3 intersections, now we're going to keep increasing K even more. So it's sliding along this axis even more. I'm going to slide it along until, say, it's all the way over here now. Okay. So I draw on my per capita growth rate G. And I see that once again, I've only got 1 intersection here. I'm going to keep this as N3 star, even though there's only 1 of them. just because this was the third equilibrium that we had on the graph before, okay? And how about the stability of this? Can anyone tell me whether this is going to be stable or unstable?
Stable.
Stable, yeah. So when we think about this, G of n is bigger than our P of n to the left. And the P of n, the predation term, is bigger on the right. So that means we move to the right when we're below n3 star and move to the left when we're above n3 star. So it is stable. So this is for a large. So a large carrying capacity for our budworms. Sorry, I keep hitting a button which minimizes my screen. Okay. I'll zoom out a bit just so we can see these three alongside each other. I'll use a ran out of space a little bit for that one on the right. The only difference here is that the red curve is staying the same. The black curve, we're just sliding this point that it intersects the horizontal axis to the right. As we do that, we go from one equilibrium, one non-trivial equilibrium, to 3, and then back down to 1. In fact, there is a point where this black curve here will intersect exactly twice. And likewise, again, there'll be a point here where it intersects exactly twice. We've gone just beyond those. Those are knife edge scenarios. So, can anyone tell me what kind of bifurcation this is? We're going from 1 to 3, and then there's a second bifurcation again where we go from 3 to 1. Exactly, it's a saddle node bifurcation. So what you can imagine here is we've got, as this black curve here, yeah, let's do it this way, just because it's a little bit easier way to think about it. We're starting from 3, say, and as I move left or right, what happens? Well, if I start moving this black curve to the left, I've got an unstable equilibrium and a stable equilibrium, and they're going to start moving towards each other as this black curve moves to the left. So they move towards each other until they meet, and then they annihilate each other, and then you're in this scenario here on the left. Likewise, if I start in this scenario, as I move this towards the right, this unstable equilibrium and this stable equilibrium at the top are going to move towards each other until this black line is tangential to this right curve. When it's a tangent, these two have met. You've got a stable and an unstable equilibrium meeting, so they collide and they annihilate each other, and then you would just end up 1 again. So you've got a saddle node bifurcation going this way and another one going this way. Okay, so let's think what that bifurcation then diagram looks like. We've already sketched a few bifurcation diagrams so far. Here we're going to be varying our parameter K. This is the carrying capacity for our budworms. This is telling us something about the resources available for our budworms and as those vary. And we want to plot our n star. What does this look like? Well, we have 3 equilibria here. Let's think about this n1 star here on the left-hand side, first of all. When K is very small, so if K was all the way over in this bottom corner here, we'd have a relatively low value. As K increases, we're going to be moving off to the right. So we have something that looks a little bit like this. It's increasing, but increasing fairly slowly. And there comes a point where K gets large enough where we're over on this right-hand side where N1 vanishes. Okay. So it's increasing, and then at some point it vanishes. Let's think about the other side. We have an N3 star here, which exists for all very, very large K. But if we start decreasing K, there'll come a point where N3 star disappears as well. So going from the other direction, this is my N3 star branch. It's decreasing, 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 and then reaches a point where it will stop. So this is my N3 star. This is my N1 star. In between that, we have an N2 star. And that N2 star is always unstable. So we know that it must meet both of these. N2 star. We see that there are two values of K1, K1 and K2, where we have these saddle node bifurcations. Typically as well, when we talk about bifurcation parameters, we talk about as a parameter increases, there is a bifurcation. There's nothing special about it increasing. It could decrease as well. Typically, we just talk about a parameter increasing, there's a bifurcation. Going back in the other way, there's a bifurcation as well. It's kind of cool when you come from this direction, say, and then all of a sudden two equilibria appear out of nothing. So a bifurcation doesn't just correspond to the fact that when they meet, they annihilate each other. Here, they appear out of nowhere. Okay. So let's think about what might happen. And what does this how does this relate back to this problem of spruce budworms? Remember at the start that every so often, every few decades, there's an explosion in the population size. So suppose we start off somewhere along this branch here. Okay. This is saying for a relatively low carrying capacity, there is some stable population size, N1 star. Okay. But suppose every so often there's a boom year where there's a lot of additional resources for these spruce budworms. So you shift from, say, being somewhere along this branch here to now maybe your K values over here. It's a little bit higher. Okay, so you've increased the carrying capacity because there are more resources for the budworms. So what's going to happen? Well, suppose you're moving along this trajectory here. So you're increasing your N1 star as the carrying capacity increases. There comes a point when K is above K2, where all of a sudden, your population is going to shoot up to this branch here. So you're increasing the carrying capacity, your N1 star is increasing a bit, increasing a bit, increases a bit. It's kind of like a catastrophic collapse, but just going in the other direction, okay? So think of it as a catastrophic increase. So the carrying capacity increases, and then you cross this threshold, and you've gone from this relatively low level of these pests, these budworms, up to this really high level. Not quite sure. Carrying capacity could keep increasing, you stay on this branch. The really interesting thing, though, is suppose what happens is if you start decreasing those resources now. So decrease these resources, suppose back to some initial level. Suppose your initial level when you first met this system, your K was here. Let's call this K0. Well, say you're back at your initial level of resources for these budworms, but you don't jump back to that N1 star. What this is basically saying is that there's some memory in the system because of this, these two equilibria here. This is known as bistability. It's bistable. Now, they're given a value of K, if you're in this bistable region, there are two possibilities as to where you'd be. And where you are going to be at depends on where you were recently. So if you started off with your initial population size somewhere down here, you stay down here. But if you had been up at this high level, you would stay at that high level. So even though there's the same amount of resources in the system, where you were recently affects where you end up, which I think is kind of cool. You kind of, I don't know, naively, you might assume that if there's a given number of resources in the system, there should be a given number of spruce budworms, right? Not a very low level and a very high level are both possible. And this all comes about because of this saturation term, or the fact that we have this attack rate and handling rate, and this functional response for the predation. Okay, so if we follow that on a little bit further, there comes a point if you keep decreasing the carrying capacity by reducing the resources. There'll come a point when K, if it falls below K1 here, there would be a catastrophic collapse. And you'd go back down to this N1 star. So you can think about sketching on what a trajectory might look like if you started increasing, like this red line, if we start increasing K, what would happen? You'd follow this N1 star, and then you'd suddenly shoot up. Maybe go along here a bit to the right as you keep increasing K. I'll draw some arrows on here to indicate the direction of travel. And then now suppose we start decreasing the carrying capacity of the budworms. What happens now? I'm going to follow this top branch here until K falls below K1, at which point I'm suddenly going to have this collapse down to this bottom branch here. So this is actually known as hysteresis. In fact, there's a couple of questions there to describe what happens. Have a go at describing it in your own time afterwards. See if you can recapitulate that argument to say, okay, what happens as you increase these carrying capacities? Okay. So I'll leave that as something for you to go over in your own time. I'm going to focus on this idea of hysteresis, though. This hysteresis is basically telling us that there is some memory to this system, okay? So where you end up depends on where you were at recently. That's the key thing with hysteresis. And this isn't just something that happens in biology. It also happens in physical sciences as well. Has anyone heard of something in electronics called a Schmidt trigger? No electronics fans here. It's fine. It's fine. It's totally fine. A Schmidt trigger is spelled like this, after a chap called Schmidt. Is a very useful thing in electronics, which has hysteresis in it. In fact, its symbol, electronic symbol, looks something like this, which should hopefully remind you of this. I go back up here. The curve that I've drawn in red is a bit similar to here. What happens with the Schmidt trigger? Suppose you've got two different voltage levels. You've got, say, 5 volts and 0 volts. If you want to convert between something that's digital and analog, suppose this is your 0 and this is your 1, if we're talking in digital, the voltages that are going on in your phone, in your laptop, everything like that, they're all actually analog, right? There's a given continuous level of voltage, but we want to convert that into something that's 0 and 1. And so you want to set a threshold, say, okay, if you're below 2.5 volts, you're at 0. And if you're above 2.5 volts, you're a binary 1. But the problem with that is what happens if you're very close to 2.5 volts? If you keep oscillating just because of a bit of noise around that 2.5 volts, you're going to be rapidly switching between binary 0s and 1s. But you don't really want that. So what you want to do really is to have a lower threshold, or if you're below that lower threshold, you go to 0, and an upper threshold, you go to 1. And if you're somewhere between that threshold, where you are is where you were before, okay? So you have a bit of memory in that, so there's a different upper and lower threshold to switching. So, it's quite a departure from biology, but this idea of having these different switching thresholds is actually something we find can be very useful in other things. This same idea of hysteresis applies. The key thing is the current state depends on the state in the past, in the recent past, that is. Okay. That is it for today. I'll stick around for a few minutes in case you guys have any questions. There's a self-study problem here about the Spruce Budworm as well for you to work through. And I'll stick around for a few minutes as well in case you have any questions about the quiz on Wednesday. Okay? If not, you're free to go. Yes.
So I think if you start around N2, which way does it go? If you start last, right?
Around N2? Very good question. It depends on whether you're above or below that dashed line. So what you can think of that as being like, suppose you've got 2 valleys and you've got a ridge between them, and you put a ball on that like close to the top. Depending on which side you started on, is which side it will fall into. So they're known as like basins of attraction because they're trapped within a basin. Kind of like as well, like 2 rivers going. If you've got water on a mountain range, you have like a water basin on one side and another. And, you know, the continental divide, whether you're going to end up that river going into the Atlantic or the Pacific, depends on which side you start on. Yeah.
For that bifurcation diagram, where is K1 and the K2 come?
Where do they come from? Very good question. So just go back up here. This K1, this K2, where do they come from? These are the points at which I'll sketch it on here. If I can, let's see where's the best place to do it. I'll do it in gray. This K1 here, that's my K1. It's the point at which this gray curve is tangential down here. So that's the point at which you just touch. So your growth rate is just reaching the predation rate, or per capita ones are. And so if you're a little bit to the left of that, you have 1 equilibrium. If you're a little bit to the right of that, you have 3. And so at this point, technically you've got 2, but you're like absolutely on a knife edge because it's just a tangent. So that's your K1. And then your K2 is, let's see, I'll draw it over on this side here. Your K2 would be there. So your K2 is here again. You're just touching here. So that's the point at where these two have moved towards each other and meet each other. Does that make sense? I'll just zoom out so you can take a photo. Any other questions?
For that bifurcation diagram, N2 it comes from the second diagram.
Yes, N2 is appears. So N2 first appears as this K moves to the right. When you grab K1, N2 and N3 suddenly appear. And then as you keep moving, N2 keeps moving up in this direction until it meets this one, and then they collide and then they disappear.
So this is mean between K1 and the K2, all N2 star value will be unstable.
Yes, exactly. So N2 star is always unstable. Yeah, because these two are always stable. You always have this unstable one between them.
And will this cover days?
I will leave that as a speculative. It might do, it might not. But mainly because I want to make sure you guys revise the breadth of material. Rather, if I tell you exactly what the quiz is on, then you won't revise all of the stuff. Yeah, in theory, anything that we've done so far can show up. Okay. One thing I'll say about the quiz as well, like if you find that it's too, and I would say this about all things, if we find it too hard or too difficult, if everyone gets, very low marks, then it suggests that I've set it too hard and I will adjust it in future. Likewise, if everyone gets 100%, then I've probably made it too easy. Okay, so if everyone finds it really, really hard, don't suddenly drop the course because you think all of the assessments are going to be hard. I will adjust things accordingly. Okay.